problem, we want to try to find the electric field due to a particular charge distribution. So the given charge distribution is an insulating sphere. So there's charge uniformly distributed inside this sphere everywhere. So rho is constant. And Q is the total charge on the sphere. The radius of the sphere is A. And we want the electric field everywhere in space from 0 until infinity. So let's review a little bit what the concept of electric flux means, or how to calculate it. If you want to calculate the total electric flux through a closed surface of any shape, and remember, the surface is a purely mathematical construction. It doesn't exist in reality. The surface is not made of any material. It's just purely virtual. And the definition of the total electric flux to this surface, and this circle indicates, on the integral, indicates that the surface is closed. It's integration of E dot dA. And remember what this integration means in terms of a limit of sums. What you do is you cut up your surface into small elements of area, as you see here. And the area vectors, now, we said area is a vector, it's not a scalar, it's a vector, and it always points from inside the surface to outside the closed surface. And so you cut up your surface into small elements of area. For each element of area, like this ith element of area, there are two vectors. One is the area vector that points perpendicular to the surface, and one is the electric field vector. This electric field could be due to any charge distribution existing in space. So the total electric flux, you go to this element of area, you take the dot product of the electric field and the area vector, and then you get a number. It could be either positive, 0, or negative, a number. Then you go to the next element of area and you do the same thing. And you add those two numbers, and you add the third number and the fourth number and fifth number. For all the elements of area, you get a number, and you add all those numbers up. When you add all those numbers up, that's what this total electric flux is. So let's also review Gauss's law. Well, Gauss's law says that if you get the total flux through a closed surface, it equals to the charge inside the surface divided by epsilon naught, which is a constant. And the electric field here is the electric field due to all charges in the universe. And so you know that means that the flux doesn't depend on the shape of the surface. If you put a point charge, for instance, at a point in space, and you make a sphere around it, a Gaussian surface of a sphere or any other shape, the flux is the same for all those surfaces. So the first thing we need to do if you want to find the electric field due to, for that insulating sphere, you need to create a Gaussian surface. You need to choose it, make it the shape you want, the size you want, and put it in the location that you want to solve the problem. But before we do this, we need to know what the direction of the electric field is, because you're going to choose your Gaussian surface based on what the electric field is happening, what's happening with the electric field in space. So let's ask the question, if I go to a point, this point in space, what is the direction of the electric field at that point? Is it pointing radially outwards or inwards, or is it pointing at some angle in general? Well, we can make a nice symmetry argument that proves that it has to be radial. So let's start the argument. The argument is going to be an argument by contradiction. So let's assume that the electric field vector is not radial. It has an angle with the radial direction. And then take the sphere of charge plus this vector and rotate them both, rotate everything about this axis. When you do that, the vector, after it's rotated 180 degrees, it becomes this vector. When you rotate the charge, the sphere, about the central axis, the charge remains exactly the same. So what we have here is a contradiction. You have two problems that have exactly the same charge distribution, but they have different electric field vectors at a point in space, and this cannot happen. So this means that you can never have a component of electric field other than the radial component. So if you have the electric field only has a radial component, no matter how you rotate the problem, the electric field vector stays the same. So we can conclude that the electric field vector must be pointing along the radial direction, either outwards or inwards, depending on the charge of the sphere. So now we know that the electric field is pointing radially outwards. This is a sketch of what it looks like at certain points in space. Now, what shape Gaussian surface would you choose based on this knowledge of the direction of the electric field? Remember, what is the basis on which we want to choose this Gaussian surface? We want to make sure that we can take the electric field outside of the integration. In order to do that, we need to get rid of the dot product. So how would you get rid of the dot product? How would you make a surface that would get rid of this dot product? Well, if we choose a spherical Gaussian surface, this dotted line represents a sphere. It's a spherical Gaussian surface. If you look at the area vectors at any point on the surface of the sphere, the area vector, which is the blue vectors, they're always in the same direction as the electric field vectors at the same point on the surface. So why is this helpful for us? Because when you look at integration of E dot dA, which means it's integration of E dA cosine theta, since the angle between the area vector and electric field vector is always 0 at every single point on the sphere, then theta is 0, and that means cosine 0 is 1. So we got rid of this cosine theta. So now we've simplified the problem and we just have integration of E dA. Now the second simplification that can happen, and that's again one of the reasons why we chose this spherical surface, is that if you calculate the electric field over here, or over here, or over here, or over here at the same radius on the surface of the Gaussian sphere, you expect that the magnitude will be the same. Of course, the direction isn't the same, but you expect the magnitude to be the same. From symmetry, there's no reason, as you walk along this sphere, there's no reason for the magnitude to change. Everything is symmetric as you go along this Gaussian surface. So you can take the electric field magnitude outside of the integration. When you do that, you're left with integration of EdA. What is integration of EdA? This is just the total surface area of the Gaussian surface, Gaussian sphere, which is 4 pi r squared. We put here E times 4 pi r squared. And on the right-hand side, we have Q inside over epsilon naught. What is the total charge inside the Gaussian sphere? Well, you can see that all the charge of the problem is inside the Gaussian sphere in this case. So we should replace Q inside by Q. And when you do that, that's the last step in the derivation. Now you just need to get the other terms on the other side and keep the electric field on the left side. And you get the result that the electric field is KE. 1 over 4 pi epsilon naught is Ke Q over r squared. And this is the same electric field as the electric field due to a point charge. Okay, now we want to find the electric field inside the sphere at some point, say r, where r is less than a. What kind of spherical Gaussian surface should we take? We should take the same kind of surface exactly, a sphere, and you should kind of justify this to yourself using the same reasoning that we did before exactly. You can reason very easily that the direction of the electric field and area vectors will also be in the same direction at every point on this Gaussian sphere. And all the arguments we used before work exactly as they do in this case. So integration of E dot dA becomes E times 4 pi r squared. Now the question is, what is Q inside? What is the total charge inside this dotted Gaussian sphere? If we get the total charge inside any volume, in the most general way to write down the charge inside any volume is integration of rho dV. Our problem, rho is a constant. The charge is uniformly distributed, so rho is constant. So I can take rho outside of the integration. That means you're left with integration of dV. What's integration of dV? It's the total volume of the Gaussian surface, which is 4 over 3 pi r cubed. Now, rho itself we can calculate separately. We can say, well, let's look at the total sphere, the whole sphere, the one that has radius a and total charge q, and let's calculate rho from that. So rho is the total charge over the total volume. So we can calculate rho independently and plug it back into here. We get this final expression. Of course, you can cancel the 4/3 pi up and down. You get this final result for Q inside. So Q inside increases as the third power of the radius. So now we can substitute Q inside, the one we got, into Gauss's law, the right-hand side of Gauss's law, and let's see what we get. We get this expression. Now you have here r cubed, you have here r squared, so you only get one r left over here. By rearranging the terms, we get this final result. Everything inside this bracket is a constant, so that means that the electric field increases linearly with r, for r less than a. So this is a summary of the result we got. When r is less than a, the electric field increases linear with distance. Once you go outside the sphere, then the electric field starts to decay like 1/r squared. If you want to calculate the electric field at A, you can use either formula, because if you put here r equal to A, you get kqa/a cubed, and when you put r equal to A here, you get kq/a squared. And of course, these two things are the same.